Hello guys, I'm Nida from cybersecurity. In today's session we are going to discuss about the partial differentiation of boolean functions. Partial differentiation is a powerful tool in mathematics that has numerous applications in the design and testing of logic circuits. In this presentation, we will explore how it works and how we can apply it to improve our designs and testing strategies. Partial differentiation of Boolean functions is a concept in mathematics that involves finding the derivatives of Boolean functions with respect to one of its variable. It's used in fields like logic design and computer science. The basics of Boolean algebra. Boolean algebra is a branch of mathematics that deals with binary variables and logic operations like AND, OR, and NOT. Partial differentiation involves taking the derivative of a function with respect to one of its variables, holding all the other variables constant. It is useful because it allows us to analyze the sensitivity of a function with respect to each variable, which is essential in the design and testing of logic circuits. The partial differentiation and Boolean functions. The Boolean functions in logic gates are used to describe the behavior of logic gates, which are the building blocks of digital circuits. The using of partial differentiation on Boolean functions is, is that by applying partial differentiation to these functions, we can get information about their behavior and sensitivity to changes in input variables. The applications of partial differentiation in circuit design. We can use this information to optimize our designs, reduce complexity, and improve performance. In the context of Boolean functions, partial differentiation is not commonly used. There are many ways to enhance the efficiency and functionality of logic gates. One approach is to use different combinations of gates to achieve the desired logic function while minimizing the number of gates used. Additionally, optimizing the arrangement of gates and their interconnections can help reduce delays and improve overall performance. Do you have a specific logic gate design in mind that you'd like to improve? If yes, then let's dive into it. Next is circuit simplification using partial differentiation. So, using partial differentiation for circuit simplification is an interesting idea, but it's not a common approach in the field of digital logic design. Partial differentiation is typically used in calculus to find derivatives and analyze continuous functions, whereas digital circuits involve discrete logic operations. However, there are other techniques like Boolean algebra, Karnoff maps, and Quine-Makluski method that are commonly used for circuit simplification. These methods can help simplify complex circuits and optimize their design. Applications in tests. Fault diagnosis and localization. Partial differentiation can be used to identify faults in a circuit by analyzing the output of the circuit for different input patterns. Test generation using partial differentiation. By analyzing the sensitivity of a circuit to its input variables, we can generate test patterns that maximize the coverage of the circuit. Quality control. Partial differentiation can be used to check the quality of a circuit by analyzing its behavior under different input conditions. There are many benefits of partial differentiation. Partial differentiation has several benefits in the field of calculus and mathematical analysis. It allows us to find the rate of change of a function with respect to a specific variable while treating other variables as constants. This can be helpful in various applications, such as optimization problems, physics, economics, and engineering. By understanding the behavior of a function in different directions, we can gain insights into its properties and make informed decisions. While partial differentiation may not be directly applicable to circuit simplification, it remains a powerful tool in many other mathematical contexts. The partial differentiation of Boolean functions. So, the Boolean functions are typically associated with logic and truth tables. In the context of Boolean functions, partial differentiation is not commonly used. Partial differentiation is a concept from calculus that involves finding the derivative of a function with respect to one variable while treating the other variables as constants. Since Boolean functions are discrete and not continuous, the concept of partial differentiation doesn't directly apply. However, there are other mathematical techniques and operations that can be used to analyze and manipulate Boolean functions. Now, let's conclude this by having the future directions for partial differentiation of Boolean functions. It is an intriguing idea to explore the future direction of partial differentiation in Boolean functions. While it is not commonly used technique in this context, there is always room for innovation and new approaches. One potential direction could be investigating how partial differentiation can be adopted or extended to analyze and optimize Boolean functions. This could involve exploring the relationship between Boolean functions and continuous functions and finding ways to apply concepts from calculus to enhance the analysis and design of Boolean circuits. It would be interesting to see how this area develops in the future. The speciality of partial differentiation in Boolean functions lies in its ability to analyze the sensitivity of a Boolean function to changes in specific variables while treating the other variables as constants. This can provide insights into the behavior and interactions of different parts of the Boolean function. By differentiating with respect to different variables, we can examine how changes in those variables affect the overall function. It can be a useful tool for understanding the behavior and optimization of complex Boolean circuits. When it comes to using partial differentiation in Boolean functions, there are a few potential disadvantages to consider. First, Boolean functions are inherently discrete and operate on binary values, while partial differentiation is a technique primarily used in calculus for continuous functions. This mismatch in nature can make it challenging to directly apply partial differentiation to Boolean functions. Additionally, Boolean functions often involve logical operations and discrete logic gates, which may not have well defined derivatives. As a result, the application of partial differentiation in this context may not always yield meaningful or practical results. It's important to consider alternative methods such as Boolean algebra and logic optimization techniques that are specifically tailored for analyzing and simplifying Boolean functions. So, we also have disadvantages for partial differentiation in Boolean functions, but there are a whole lot of benefits of partial differentiation in Boolean functions, and we have also discussed the direction for future of partial differentiation in Boolean functions. Thank you.